This is Leetcode 3640 Trionic Array II. It looks like a subarray problem, but the real challenge is tracking 3 phases of monotonic behavior in one pass. If you understand this solution, you understand state-based DP at an interview level. You're given an integer array. A trionic subarray is a contiguous subarray that has 3 strict phases. 1. Strictly increasing. 2. Strictly decreasing. 3. Strictly increasing. Your task is to return the maximum possible sum of any such subarray. It's guaranteed at least one valid trionic subarray exists. Let's walk through example. Example. Nums equals 1, 4, 2, 7. Choose 1, 4 increasing, 4, 2 decreasing, 2, 7 increasing. Sum 1 plus 4 plus 2 plus 7 is equal to 14. Every phase must be strict. Equal values immediately break the sequence. This is not a sliding window problem. The boundaries are not fixed. Instead, this is a state-based dynamic programming problem where each element transitions between phases. We track 3 states at every index. At every position, we maintain 3 values. Inc. Best sum of a subarray ending here that is strictly increasing. Dec. Best sum ending here that is increasing decreasing. Try. Best sum ending here that is a complete trionic subarray. Only try represents a valid answer. A brute force approach would try all L, P, Q are combinations. That's O of n. Completely impossible for n equals 100,000. We need one pass, constant memory. We compare cur with prev. Case 1, cur greater than previously increasing. We can either extend or start fresh. Next inc is equal to the maximum of inc and previous plus cur. And this may also complete or extend a trionic sequence. Next try is equal to the maximum of dec and try plus cur. Case 2 cur less than previous decreasing. This can only happen after an increase. Next dec is equal to the maximum of inc and dec plus cur. Case 3 cur equal to previous. Equal values break strict monotonicity. All states reset. The function finds the maximum sum of a trionic subsequence in a list of numbers. A trionic subsequence has 3 phases: increasing, decreasing, increasing again. Meaning of the variables. Inc. The best sum so far for a subsequence that is currently increasing. Dec. The best sum so far for a subsequence that is currently decreasing. Try. The best sum so far for a subsequence that has completed. Increase, decrease, increase. Best. The maximum trionic sum found overall. Previous. The previous number in the array. Cur. The current number being processed. All sums start at -infinity to represent not yet possible. Step-by-step logic. Initialize all states, inc, dec, try, best, to -infinity. Set previous to the first number in the list. Iterate through the remaining numbers one by one. For each current number, reset the next states, next inc, next dec, next try, to -infinity. If the current number is greater than the previous number, you can continue or start an increasing sequence. Take the larger of the previous increasing sum or the previous value, then add the current value. Continue the final increasing phase of a trionic sequence. Take the larger of the decreasing or trionic sum, then add the current value. If the current number is less than the previous number, you can continue or start a decreasing sequence. Take the larger of the increasing or decreasing sum, then add the current value. After processing the current number, update inc, dec, and try with their new values. Update best with the maximum trionic sum seen so far. Set previous to the current number. Final result. After all numbers are processed, return best, which is the maximum sum of any valid trionic subsequence. At every index, we only keep the best possible sum for each valid phase. No backtracking, no nested loops. Every state is updated in O of 1 time. Time complexity, O of n. Space complexity, O of 1. That's optimal. Common mistakes. Allowing equal to instead of strict, greater than or less than. Forgetting that try must come from dec. Treating this like a sliding window, not resetting on equal values. This problem tests whether you can model phases with DP states, handle strict conditions, write clean one-pass logic. If you can explain this transition logic clearly, you're operating at senior interview level. See you in the next one.